p, 2ap, comma ap squared, and q, 2aq, comma aq squared, are points on the parabola x squared equals 4ay. The chord PQ varies in such a way as to always pass through the point 0, negative 3a. Part I. The tangents at P and Q meet in T. Find the locus of T. In Part 2. The normals at P and Q meet in N. Find the locus of N. Okay, so here we have an example of a locus problem in which we have two variables, namely the parameters little p and little q. In order to do these types of questions, you need to establish a relationship between these two parameters. And usually that comes with the first part of the question. In our case, it tells us that the chord PQ always passes through a certain point. You might get something like it's going to be a focal chord, which means it would pass through, obviously, the focus. You might get something that says that two lines meet at right angles, or two lines are perpendicular, or something like that, but there'll always be a bit of information which allows you to relate little p and little q to each other. So how are we going to get our relationship? Well, if the chord PQ varies in such a way that it always passes through this point, then what's the equation of PQ? Well, we've seen that in previous videos before, so I'm not going to derive it here, but that's y equals p plus q on 2 multiplied by x minus APQ. And if this point passes through this line, if this line passes through this point, that means this should satisfy the equation of the line. So I can substitute that in, and I'll get negative 3a equals, this term will become 0 because x is 0, minus AP cubed, and divide by negative a, and I'll get 3 equals PQ. And so there you can see I have my relationship between P and Q. The relationship is that when I multiply them together, I get 3. Good, so now that I have that relationship, I can start to answer the question. It says that tangents at P and Q meet in T. Find the locus of T. So to find the locus of T, I'm going to need the equation, or the coordinates of T. So, the coordinates of T are where the tangents meet. Now, the equation of the tangent at P, which again we have derived before, so I'm not going to do it in this video, but if you were given this question in an exam without being given the equations of the tangents or the chord, or later on we'll see the normals, you'll have to derive those. Have to stress that, because otherwise you will lose marks. So the equation of the tangent, I should say at P, is going to be y equals px minus ap squared, and similarly at Q, y equals qx minus aq squared. Okay, now let me solve these simultaneously to find the equation or the coordinates of T. So substituting 1 into 2, I will get px minus ap squared equals qx minus aq squared. Bringing this term over here and this term over here, and factorizing in the same step. So I'll get p minus q multiplied by x equals, now here I'll have ap squared minus aq squared. I can factor out an a, and I'll be left with p squared minus q squared. And then I can factor this as a difference of two squares, and I'm left with a times p minus q times p plus q. And now I can cancel this p minus q with this p minus q, and I'll be left with x equals a times p plus q. So I have my x coordinate of the point T. To find the y coordinate, I substitute into either 1 or 2. It will give me the same answer. And I get the following. Y equals p multiplied by a into p plus q minus ap squared, which equals ap squared plus apq minus ap squared. This cancels with this, and I'm left with apq is y. But what do I know about y? What do I know about pq? That's equal to 3. That's in my relationship here, so let me call this a star because it's important. So from star, I get that y equals 3a. And so therefore T is a p plus q, comma 3a. And now I can see that the y coordinate, which is 3a, is independent of the two parameters p and q. So no matter how much I change the points p and q, or in other words, changing the parameters little p and little q, the y coordinate is always going to be 3a. And so therefore that is my locus as the points p and q vary. So therefore, the locus of t is the line y equals 3a. Now there is a small restriction here that most people would probably overlook. Now if I drew a parabola, very rough parabola here, so something that's like this, this would be maybe my focus here. Now my focus is a distance of a, so 0, negative 3a would be here. I can see that I always have to have p and q, because my chord PQ has to pass through this point, they always should be on the same side in order for that condition to hold. So, okay, this is a bit off, but something like that. So I have p here, I have q here. Now the tangents to p and q are always going to meet outside of the parabola. So my locus would be something like this. Let's use a different color. This would be my locus, this line. Oh, not necessarily going through P, so don't, that's just bad diagram. So this is my locus here. This is the point 3a. Y equals 3a. This is the line y equals 3a. There's my locus. But it would have to be only the parts that are outside of the parabola, because tangents can't meet inside a parabola. So therefore the locus are the point, or is the line, the segments of the line, that's the word I'm looking for. It's the segments of the line outside of the parabola. So that should be noted as well. Now for part 2. Part 2 says, the normals at p and q meet in N, find the locus of N. So we're going to need to find the coordinates of N in order to find the locus of N. And to find the coordinates of N, we need to solve the normals of p and q simultaneously. So let's put that away. Here, again, I've proven these in previous videos, so I'm not going to reprove them again, but in an exam, you definitely have to derive them if you're not given them. So here we have the equations of the normals at p and q. I've labeled them equations 3 and 4. I need to solve these simultaneously. How can I do that? Well, I think I will subtract 4 from 3. Or 3 from 4, it doesn't matter. But the reason I do that is because I can see that will eliminate one of my variables, x. So, doing that, I'll have py minus qy equals ap cubed plus 2ap minus aq cubed minus 2aq. Here I can factor out a y, and I'll have p minus qy equals. Here I can see I can factor out an a from all terms. But I'm going to do a little bit differently to that. I'm going to factor out an a from the cubed terms, so p cubed minus q cubed. And here I'm going to factor out a 2a from the remaining terms, so plus 2a p minus q. The reason I've done that is because here I have a p minus q, here I have a p minus q, and here I have a hidden p minus q, because this is really a difference of two cubes. So this is one of the first things you learn in prelim. It's a p minus q, p squared plus pq plus q squared. So that's the factorization of the difference of cubes, and then 2a p minus q. And now I can see that I can cancel p minus q from each term. Gone, gone, gone. And I have y equals a times this plus 2a. I can factor out an a from what's left here and what's left here, and I'll have a into p squared plus pq plus q squared plus 2. Now, what is pq? pq is 3 because that was our relationship from STAR. So, here I have pq is 3 plus 2, that'll give me 5. So I have a into p squared plus q squared plus 5 equals y. So there I have my y coordinate. As messy as it looks, that's my y coordinate. Now I need to find the x coordinate, so I need to substitute this into either 3 or 4. Again, they'll give me the same answer. It doesn't matter which one. So I'll sub it into 3, p squared, q squared, 5, into 3 gives me x plus a times p into p squared plus q squared plus 5 equals ap cubed plus 2ap. That'll give me x plus ap cubed plus apq squared plus 5ap equals ap cubed plus 2ap. Okay, I can see ap cubed will cancel with ap cubed. Here I'll have x plus apq squared. Bringing this 2ap over will become 5ap minus 2ap, so I'll have plus 3ap equals 0. Now apq squared is the same as apq times q. So embedded in here I have a pq, and again I know pq is equal to 3, so I have x plus 3aq plus 3ap equals 0. And so x equals, bringing these over to the other side and factoring out 3a, gives me p plus q. So therefore, my point N has coordinates negative 3a into p plus q, comma a, p squared plus q squared plus 5, close brackets. Okay, now I need to eliminate p and q in order to get a Cartesian relationship between x and y. So if x is negative 3a into p plus q, then I can say that x, or negative x divided by 3a, is equal to p plus q. What else can I say? I can say that y equals a into p squared plus q squared plus 5. I can divide by a, y on a, and then subtract by 5, equals p squared plus q squared. And now hopefully you know the relationship between eliminating p plus q, eliminating parameters when you have p plus q and p squared plus q squared. You need to consider this expression. And this is a good thing to remember because it's used in a few topics. It's used in parametrics, as we're seeing here. It's also used in polynomials and just other general algebraic manipulations. So p plus q all squared is equal to p squared plus 2pq plus q squared. Now again I can see another pq, which I know is equal to 3, so I'll have p squared plus q squared plus 2 times 3, which is 6. And now I can see that here I have a p plus q, so I can substitute this expression in, and I have a p squared plus q squared, so I can substitute that expression in, and that will have eliminated my variables p and q. So I'm left with minus x divided by 3a all squared equals p squared plus q squared is y over a minus 5, y on a minus 5 plus 6. Here I will have x squared divided by 9a squared equals y on a, negative 5 plus 6 is 1. Let's move that up. Multiply through by 9a squared, I'll have x squared equals 9ay plus 9a squared. That's fine, I could leave it like this, but it's nice to have it in the normal form, so factoring out 9a, I have y plus a. So there is my equation for the locus of n. If I wanted to, this is in the form of x squared equals 4ay, or y minus y1. That's just a shift. So I could read off the focus, the directrix, and all those other properties of the parabola if I was required to.